Okay, this is quite a short video. This one is about how can we link boiling point and the size of a molecule. So it would be great if you could stop and think, what's going to happen to my boiling point as I make my molecule bigger? Yeah, so just stop, you can pause it, you can have a think, write down a guess. That's always the best. What do you think the relationship is? As you make that molecule bigger, what's going to happen to the temperature at which it boils, at which it becomes a gas? All right, let's have a look and see if you were correct. Have a look at the relative molecular mass of hydrogen here. It's very, very low. Yeah, so the relative molecular mass of hydrogen is really low. It's only 2. Yeah, you can figure that out. This is your MR. You've got 2 hydrogens. Each one of them has a relative atomic mass of 1. So add them together and you get 2. Now its boiling point and its melting point are really, really low. Okay, really, really low. Let's go up a bit bigger and look at chlorine gas. So chlorine gas has a molecular mass of about 70, and have a look at its boiling point, minus 34, same with its melting point. But we're mostly going to focus on the relationship between boiling point because so many of these are gases at room temperature. Now, finally, we're going to look at another halogen, and that is iodine. Now, iodine has a boiling point of 184. So let's just stop and think about this, and I'm going to draw you a little table here between these ones here because this is going to help us. So this is temperature. This here is the boiling point, and this here is the melting point. So let's have a look at chlorine. So let's put the chlorine temperature. So its boiling point is minus 34. And its melting point is minus 10. Yeah, and that's higher, isn't it? So this number is higher. So if you cooled the substance to say minus 25, what state of matter would it be in? So pause, give it a go. All right, so it's higher than the boiling point. Actually, I'm going to do this around the other way. So let's draw this around the other way just to make it a bit clearer. So this here is my so we've got increase in temperature here. No, we had it right together, but I'm just going to make it a little bit clearer. So the melting point down here, I'm going to choose bromine just because it's a bit easier to see the difference in size. So this is bromine gas. Its melting point is minus 7. Its boiling point is 59. If you heated it up to somewhere in this range here, that means it's gone from being a solid to a liquid. Yeah, and then if you heat it above this, it becomes a gas. And so this is a nice little table that you can draw just to figure out what state we're in at any given time. So if you have a look at iodine here, yeah, iodine has a relative molecular mass of 234. It has a melting point of 114 degrees. So what state at room temperature is this going to be? Give it a guess. Pause if you need to. I'm hoping that you came back and said that that was going to be a solid at room temp. And that's because this number, this melting point number, is significantly higher than the room temperature. What about bromine? So bromine, which is an example over here, room temperature is about 25 degrees. So what are we going to get? Bromine should be a liquid at room temp. What do we see with chlorine? Its melting point and its boiling point really, really low. So this one is going to be a gas. Okay, so you can see there that we can use this little graph on the side here to help me. So the table, let's go into your notes on molecular size. So under the heading molecular size, the table below shows bigger molecules have higher melting and boiling points. Okay, that means that the strength of the dispersion forces must be larger. So strength of, let's just clear this off. strength of dispersion forces larger. Now, I want you to think, have a look at these two pictures. Why is the strength of dispersion forces larger in a larger molecule? Simply the size. Yeah, there's more likely that some of those electrons are going to be on either side or all on one side, and so therefore it's going to create a greater difference in electronegativity and a greater difference in that charge. So it says the strength of the dispersion forces must be larger in the bigger molecules. Dispersion forces arise between all molecules, which is what we said before. However, larger molecules have more sites. Yeah, they have more sites where minute temporary changes can develop. So here is your small one on the right here. This one has less sites, therefore the strength of those dispersion forces is going to be less, and therefore they're more likely to be able to boil, yeah, and separate apart from each other without as much energy. So more sites or electrons available in the larger molecule for the dispersion forces to act. Now, I want you to pause and I want you to try and order the following molecules from lowest to highest boiling point. Okay, so I'm going to pause too, and then we're going to see if you can get them right. Think about what was the relationship in this previous slide. What did we see? In order to order them by their boiling point or their melting point, what might we need to calculate? So I'm going to pause now. All right, so let's give it a go. What is the first thing that you did? What I'm hoping you're going to say is that you've gone through and figured out what the MR of each one of these is. So I'm just going to go through. If you haven't done that, pause and do it yourself and see if you can get there. So the first one, 1, 5, 4. This one is 2. This one is 180. This one is 38. This one is 18. And this one is 44. Okay, so that should be the first thing that you do. The next thing is we're going to order them from biggest to smallest. So let's see. We go H2 should have the lowest boiling point because it's the smallest, followed by H2O, followed by F2, followed by CO2, followed by CCl4, followed by C6H12O6. All right, let's check our answers. So to check our answers, you need to look up the boiling points of each one of these, but I've already got them, so yay! This one is minus 259. This one is 100 degrees. This one is, where are we? Minus 188. This one is minus 79. What are we noticing about these numbers? 76. And then glucose is really special. Its melting point is 146 degrees, and that's because larger than that, it tends to decompose. So overall, you can see them raising. Now, there is an exception here, and that's this guy. What is this one? This one is water. So I want you to keep that in mind, and we're going to come back to why it doesn't fit our pattern. Water is really cool. And there's a very good reason as to why it's there. So if we're going to justify the rest of our pattern, ignoring water, what would my pattern be in terms of dispersion forces? So as you increase in molecular size, so increase MR, you're going to increase the number of dispersion forces, and therefore increase the energy required to break forces, and we get an increase in BP. Okay, really nice, simple, walk you through kind of response to that question. And that is the end of our link between boiling point and molecular size.